You know when a child constantly asks the question, why, after every answer? Maddening, right? Particle physicist Harry Cliff admits he was probably that kind of kid.
You kind of end up either a physicist or a cosmologist. And so that's the kind of mentality, I think. It's that kind of curiosity about the world. And I think I was one of those kids who was probably exhausted my parents by continually asking questions.
Today, Cliff is based at the University of Cambridge, where he works on the Large Hadron Collider. He's also the author of Space Oddities, the mysterious anomalies challenging our understanding of the universe.
Particle physics is really about the most basic building blocks of the world. So essentially, deep, deep down, what is the world around us made from? And how can we understand the world in terms of basically a very small number of basic building blocks and some quite simple rules that govern their behavior. And that's really what we're trying to do. We're trying to come up with what is reality deep, deep down.
Cliff says there are two theoretical models that describe our world. There's the study of the infinitesimally small. That's the standard model of particle physics, which describes what atoms are made of. Then, on the opposite end of the spectrum, there's the standard cosmological model, which describes the universe. Simply put, it's how stars and galaxies behave and how gravity works.
The problem is these two theories don't play well with each other. But basically, the evidence from astronomy is telling us that 95% of what is out there in the universe is invisible, mysterious stuff that we call dark matter and dark energy. And we have no idea as particle physicists what these things are. So we're in this really weird position of not knowing what 95% of the universe is made from. So we think that there must be more to these pictures than we've been able to fill in so far. And as a scientist, when you see something that doesn't fit your picture, that's the most exciting thing, because it's usually the thing that doesn't fit that is the clue to the next big breakthrough in our understanding. So the book is really about chasing down these weird little effects that we're seeing in experiments and trying to figure out, are they a clue to like a radical new view of the universe?
One example of a scientific anomaly that led to a huge discovery takes us back to the 1960s. It all started when two American radio astronomers named Arno Penzias and Robert Wilson built a huge radio antenna in a suburb in New Jersey.
So you imagine this thing, it looks like a big funnel, basically, big metal funnel. And it's on a rotating turntable. But what it was essentially a radio telescope. So it's a way of looking at the sky and studying it in radio waves. And they were planning to do radio astronomy of the Milky Way and distant stars and various other objects. But when they were turning their radio antenna on for the first time, they picked up this really irritating background buzz, this kind of microwave noise, effectively, in their instrument. It's a bit like turning the radio on and there's this nasty crackling static that's interfering with your piece of music. And they're like, oh, okay, we're not going to be able to do any observations because of this noise.
Penzias and Wilson spent a year trying to figure out what was causing it. They climbed into the huge radio antenna and discovered a nest of pigeons roosting inside. After cleaning up the mess and racking their brains, they still weren't able to get rid of the static. It was a chance conversation that one of them had at a nearby university where another physicist said, I think this strange anomaly, this noise you've picked up in your radio antenna, is actually the echo of the Big Bang.
In the 60s, there was still a big debate about the origins of the universe. There was this theory known as the Big Bang theory, that the universe began with this as a sort of very, very small, hot, dense state that expanded rapidly to give birth to the universe as we know it. But there was another view, which was the steady state theory, which is that the universe had always been here and has been expanding forever. And basically new stuff kind of appears and fills in the gaps. So the universe is eternal and doesn't change. And this signal that they'd picked up was actually the light from the fireball that filled the universe 13.8 billion years ago. And over the intervening period of time had been stretched from a short wavelength hot white light to a very cold microwave noise, essentially. And this discovery settled the argument. It ended the debate. And we now accept that the Big Bang really happened.
Cliff believes this is the most profound discovery in the history of science. Namely, that the universe began with the Big Bang.
And that came from this paying attention to this funny noise in a scientific instrument. And that is the power of anomalies. So anomalies sometimes, and a lot of the time, most of the time actually, they are mundane. Usually it's pigeon poo. That's the explanation. But every so often, it's not pigeon poo, it's something really profound, like the discovery of the light from the Big Bang. So that's why these anomalies are so interesting to study, because they every so often are this little gateway, this little doorway to a new way of looking at nature.
One of the anomalies that puzzles astronomers today, which also ties back to the Big Bang theory, is the rate at which the universe is expanding. In the 1960s, cosmologists assumed that after the Big Bang, gravity would cause the expansion of the universe to slow down. But in the 1990s, researchers discovered that rather than slowing down, the expansion of the universe is accelerating. Here's how they measure that rate.
And there are basically two ways of doing this. One is you look at objects in the night sky like galaxies. You use very clever techniques to figure out how far away they are and how fast they're moving, and that allows you to measure the expansion rate of the universe. The other way, though, is you can look at this light from the Big Bang, so this noise that Penzias and Wilson discovered in 1964, and by analyzing the patterns in that light, you can work out what the universe was like very early on. So in the first, 400,000 years of the universe's history. And then you can use our theory of cosmology to run the clock forward to today and predict how fast the universe should be expanding.
But it turns out that the prediction and the measurement don't agree by quite a lot. Cliff says this irregularity suggests there's something big missing from our theory of the universe.
What this is, we do not know yet, but it could be, assuming this is a real effect, it could be some new kind of force in the universe that has shaped it through its history. It could be that this other stuff that we know is out there called dark matter. Perhaps dark matter is much more complicated than we imagined, that it's able to interact with itself, do all kinds of interesting things. It could even be that our theory of gravity is wrong. So it's potentially quite a big deal. This anomaly is still debated, but if it's real, it could be the clue that we're missing something pretty big in our understanding of the universe and its history.
You might be wondering at this point, why is any of this important? What difference does it make in the grand scheme of things?
If you ask scientists why they do this, particularly particle physicists and cosmologists, the reason is it's basic curiosity. So it's this, human beings want to know about the world that we live in. And that's ultimately why we do this research. And that knowledge in itself, I think, has huge value, cultural value as well as scientific. I mean, I think understanding our place in the universe, where we've come from, that I think does have an impact on people's lives, how they think about their lives and, what their lives mean. So it has all these sort of knock-on effects. But more practically, there have been many, many, many real-world impacts from this kind of research.
One example is a particle physics experiment in the 1930s, when the atom was first split using a particle accelerator.
In 1932, at the lab that I work in Cambridge, at the Cavendish Laboratory, Ernest Rutherford, who was a leading nuclear physicist, and his team split the atom for the first time. And this was reported all over the international press, and journalists got very excited and said, Professor Rutherford, could we be using the energy from the nucleus to sort of power our lives? And Rutherford said, nonsense, no, we're never going to get energy out of the nucleus. And then within a decade or so, you have the atom bomb, you have nuclear energy. So this fundamental research, often the impact of it is very hard to predict. But when it does come, it can be really transformative. Nuclear energy is one example. Another is, the discovery of the electron, which is the first particle that we ever found. Again, the discoverer of the electron said, this is just a scientific curiosity. This is a kind of end of the 19th century. It's never going to be any use to anyone. But you couldn't imagine the technology that we use today without understanding electrons.
American science fiction novelist Isaac Asimov said, "The most exciting phrase to hear in science, the one that triggers new discoveries, is not eureka, but that's funny." Harry Cliff's book, Space Oddities, The Mysterious Anomalies Challenging Our Understanding of the Universe, is available now online and in select bookstores. To find out more about our guests this week, visit viewpointsradio.org. For more behind the scenes and to support our show, follow Viewpoints Radio on Instagram, X, and Facebook. This segment was written and produced by Polly Hansen. Our executive producer is Amira Zaveri. Our studio manager is Jason Dickey. I'm Marty Peterson.